Comparing thermodynamic processes. In a cylinder, 1.2 moles of an ideal monatomic gas, initially at 3.6 times 10 to 5 pascals and 300 Kelvin, expands until its volume triples. Compute the work done by the gas if the expansion is isothermal, adiabatic, isobaric. Show each process in a PV diagram, in which case is the absolute value of the heat transfer greatest, least, in which case is the absolute value of the change in internal energy of the gas greatest and least. So let's note the givens first. We have N equals 1.2 moles, 1.2 moles of gas. Initial pressure is 3.60 times 10 to 5 pascals. Initial temperature is 300 Kelvin. And this tells us that using ideal gas law, PV equals nRT. So nRT initial divided by P initial is 1.2 R 300 divided by 3.6 times 10 to 5. So we can see that V initial is equal to 0.001 R. This is in meter cube. And V final is 3V initial. It is 0.003 R because I was told that the volume triples. And I also know that this is an ideal monatomic gas. So this is monatomic. Therefore, CV must be equal to 3 over 2R. CP must be equal to 5 over 2R. Gamma must be equal to 5 over 3. Let's start with isothermal expansion. Part A. So we want to calculate the work done in the isothermal expansion process. Now the work done on the gas is minus the integral from initial volume to final volume, 3V initial, nRT divided by V, and the temperature is constant here because it's isothermal, nRT initial divided by V dV. So it's minus integral P dV. And this will be equal to nRT initial. Because of the minus sign, it's instead of having natural logarithm 3VI over I, we have VI over 3VI. So that's operating the minus sign on the natural logarithm. And this gives us minus nRT initial natural logarithm 3, because natural logarithm of 1 over 3 is minus natural logarithm 3. So here I have cancelled the initial volumes. Now, if I substitute the numbers here for the work done on the gas, it is minus 1.2 times the gas constant, 8.315 joules per mole Kelvin. Initial temperature is 300 Kelvin, natural logarithm 3, that is minus 3,289 joules of work done on the gas. The question was asking me work done by the gas. So work done by the gas will be approximately 3,290 joules. I have reduced it to 3 significant figures. That's the minimum number of significant figures I have given to me. So that is 3,290 joules of work done by the gas. Part B is adiabatic expansion. And in the adiabatic expansion process, we can write T initial, V initial to gamma minus 1 is T final, V final to gamma minus 1. And I know that V final is equal to 3V initial, and therefore I can see that T final will be equal to T initial times V initial over V final to gamma minus 1, which is 1 over 3 to gamma minus 1, and gamma is 5 over 3 for monatomic gas. And what would be gamma minus 1? Gamma minus 1 is 2 over 3. So if you substitute here for T final, you will find 300 times 1 over 3 to the power 2 over 3, which is 300 times 3 to the power minus 2 over 3, and that is 144 Kelvin. Now you may ask, why did you calculate this temperature at the end of the adiabatic process? Because in the previous problem, when I was asked to calculate the work done on the gas, you see I have done a lot of work in order to get the answer, because this integration is quite cumbersome. So what I will do instead here is to show you an alternative method, which is to go with the change in the internal energy. Since internal energy is a state variable, it doesn't matter how I go from initial state to final state. So I can always do the same thing using an isobolumetric process, in which case the internal energy change will be NCV delta T. So if I substitute the numbers, it's 1.2 moles, 3 over 2R multiplied by delta T, final temperature 144, initial temperature 300. This gives us 0.6 times 3 times gas constant 8.315. The delta T is minus 156, which is equal to minus 2330 joules. So work done on the gas must be equal to minus 2330 joules, because Q is equal to 0. It's adiabatic process, and delta E internal is Q plus W, which is work done on the gas. And therefore work done by the gas in the adiabatic process is plus 2330 joules. It's an adiabatic expansion. Part C is isobaric expansion. So if it's an isobaric expansion, that's the easiest one to calculate the work done. Work done will be equal to minus P delta V. Pressure is a constant. So this is going to be minus 3.6 times 10 to 5 pascals. The delta V, as you can see here, is V final is 0.003 R, 0.001 R is V initial. It would be 0.002 R. So 0.002 times 8.315, which gives us minus 5,986 joules. And P initial, V initial, T initial with the isobaric process has to become 3V initial with 3T initial. So you can see that the temperature is also tripled in this process, by the way. And what is the work done by the gas? It would be reduced to three significant figures, 5,990 joules. So we have calculated the work done for all of these processes. If we compare these numbers, you can see isobaric is greater than isothermal, it's greater than adiabatic. So comparing the work done, isobaric is the largest one, greater than isothermal, and that's greater than adiabatic, which also makes sense because it's the area under the PV curve. Because the adiabatic one is the steepest decrease, it will have less area under it. Isobaric is the maximum area you can have, so that's the highest possible work. Now, in part D, we're talking about the internal energy change. So what is the internal energy change in an isothermal process? If the temperature of the system is not changing and the number of moles is not changing, which are the only two variables that affect internal temperature, internal energy change must be equal to 0 for isothermal process, which means that the heat added is minus the work done on the gas, which is plus the work done by the gas, which is 3290 joules. That's what we calculated in part A. So Q, heat added, is equal to the work done by the gas. Now in the adiabatic process, we know that the heat added is 0, and in the isobaric process, we know that heat added is NCP delta T, which is 1 over 2 times 5 over 2R times delta T. Now delta T, as you can see here, is Ti to 3Ti, 2Ti, which is 2 times 300 Kelvin, which is roughly 15,000 joules. So comparing the heats added to the system, the maximum one is isobaric. The heat added in the isothermal process is less, and heat added in the adiabatic process is least. It's the basically by definition 0 heat added in this process. Okay, so I have to make this my final answer for this part. And let me check. D, show each case process in a PV diagram and talk about the absolute value of heat transfer. Now I have to also show these in a PV diagram. Now, if I look at the isothermal process, so this is an isotherm, P initial, V initial will become, because I have the same temperature, PV is equal to nRT, Pi over 3V initial, so that their product will be a constant. So this is a P times V is a constant curve. That constant is nRT. In the adiabatic process, PV to gamma is a constant. So if I have P initial, V initial to gamma is P final 3V initial, which is V final to gamma, I find that final pressure should be P initial divided by 3 to the power gamma. So this will be Pi over 3 to the power gamma. And in the isobaric process, I have the same pressure, Pi, which is a constant, and the volume is increasing. So that's what I would see in a diagram. And you will see that the adiabatic one is a steeper fall. So if I plot them on the same graph, this would be isobaric, this would be isothermal, this would be adiabatic. So that's an even steeper curve. Now, part E is asking me about internal energy. The internal energy change using first law of thermodynamics is heat added plus the work done on the gas. In the isothermal process, internal energy change is 0 because the temperature change is 0 and the number of moles don't change. In the adiabatic process, we have an internal energy change which is equal to the work done on the gas. which is minus 2330 joules. And in the isobaric process, the internal energy change is the work done on the gas plus heat added to the gas. How much heat was added? It was 15,000 joules in the isobaric process, so 15,000. And work done on the gas in the isobaric process we have found to be minus 5,986 joules. So this was minus 5,986 joules, 9,014 joules. So what I want to compare in part E is the absolute value of internal energy change. Okay, so if you look at the numbers, the absolute value of internal energy change is greatest for the isobaric process, you can see, and then follows the adiabatic one, and the least internal energy change, which is 0, is the one of isothermal process. So this basically completes our comparison of these three processes that achieve the same task of tripling the volume. So they're all expansion processes. Let's summarize what we did here. We talked about 1.2 moles of an ideal monatomic gas with an initial pressure 3.6 10 to 5 pascals, 300 K, temperature expanding to have its volume tripled. We computed the work done on the gas if the expansion is isothermal, adiabatic, isobaric, and then also we calculated heat transfer and the absolute value of internal energy change, and then we also showed these processes on a PV diagram. Since it's a monatomic gas, Cv is 3 over 2R, Cp is 5 over 2R, gamma is 5 over 3. Only degrees of freedom that contribute to the internal energy are translations of the center of mass. And I can see that the initial volume, because it's an ideal gas, obeys the ideal gas law as the equation of state. PI is equal to nRTI. This gives me initial volume 0.001 R, final volume 0.003 R. R is the universal gas constant. Isothermal expansion, work is minus integral P dV. P is nRT initial over V. T initial is a constant here. It's constant temperature process. So I obtain minus nRT initial natural log 3. This is work done on the gas, by the gas. I have to multiply by minus 1, 3,290 joules. Adiabatic expansion, instead of calculating the work done by using minus integral P dV, I have figured out what would the final temperature be. It is 144 Kelvin. Using this relationship, TV to gamma minus 1 is a constant. So I have two things for adiabatic process. PV to gamma is a constant and TV to gamma minus 1 is a constant. Knowing the final temperature is 144, initial temperature is 300 Kelvin, and the internal energy change can always be calculated using an isovolumetric process with the same temperature change, because it's just a function of N and T, I obtain minus 2,330 joules, noting Cv is 3 over 2R for monatomic gas. And Q is equal to 0, adiabatic process, therefore internal energy change is due to work done on the gas, which is minus, so by the gas will be plus 2,330 joules. Isobaric expansion, since P is not a function of volume, it comes out of the integral, it becomes minus P delta V, and the temperature change in the isobaric expansion is Ti to 3Ti in order to maintain the equation of state. And work done by the gas is minus the work done on the gas. In my final answer, I always reduce to 3 significant figures, the minimum number of significant figures I have in the problem statement. This shows that isobaric process with the largest area underneath it gives the largest work. The smallest area is given by the steepest decrease adiabatic process, that's here, and isothermal is in between. And for the isothermal process, since the internal energy change is zero, heat added is minus the work done on the gas. So work done on the gas was minus 3290 joules. So that is basically work minus the work done on the gas becomes work done by the gas, 3290 joules. Adiabatic process, no heat. By definition, isobaric process, Q is equal to NCP delta T, and Cp is 5/2R, and that gives me 15,000 joules. So we can see isobaric process heat added is greater than isothermal, greater than adiabatic, which is 0. Then I have looked at what is the final pressure of the isothermal process. Because pressure times volume product is a constant, it has to be Pi/3 at the final state. For the adiabatic process, PV to gamma is a constant. That means P initial/3 to gamma is the final pressure. In the isobaric process, it's the same pressure during the expansion. And finally, for the internal energy change, isothermal process, by definition, delta T is 0, and if there's no gas molecule leaking out, internal energy change is 0. Adiabatic process, the internal energy change is equal to the work done on the gas because heat added is 0. So that's minus 2330 joules. Isobaric process, there is both work and heat. Heat was calculated here. Work done on the gas was calculated here. So the total internal energy change for isobaric process is 9014 joules. So in absolute value, isobaric is greatest, isothermal is least, adiabatic is in between.